Quite a few of these videos have involved me talking about design patterns. So we've seen things like the strategy pattern, the repository pattern, the mock object pattern. And actually this year, 2020, is the 25th anniversary of the publication of the book that really brought design patterns into software development. That was this book, Design Patterns, Elements of Reusable Object-Oriented Software by Eric Gamma, Richard Helm, Ralph Johnson and John Vlissides. It's difficult to remember those names, and so they're very often referred to as the Gang of Four or even the GOF. And when we talk about specific patterns coming from that book, then they're often referred to just as GOF patterns. And so strategy, for example, is a Gang of Four pattern, whereas repository and mock object are ones that have come along later. So as well as introducing to us the idea of patterns, it also allowed us to start having more and more patterns being discovered and invented as time goes by. The pattern I want to talk to you about today is actually a Gang of Four pattern, the state pattern. And when the state pattern is useful is when you have stateful objects. For example, consider an aircraft. Now, an aircraft could be in one of two possible states. We could either have our aircraft on the ground or we could have it in the air. And the key thing is it responds very differently to commands when it's in those two states. So if it's on the ground and we tell it to raise its undercarriage, then obviously it shouldn't do that. Whereas if it's in the air and we tell it to raise its undercarriage, then that's fine. Or on the other hand, if we had two states of, say, flying at 13,000 feet and flying at 15,000 feet, well, although they're different states, they're not substantially different. It would still behave in the same way. So we talk about states in terms of states that significantly affect the behavior. Another example from a completely different area, if you remember the classic game Pac-Man, if you consider one of the ghosts in Pac-Man, its normal state would be that it's displayed a particular colour, it tries to chase the Pac-Man, and if it catches the Pac-Man, it kills him. On the other hand, when the Pac-Man eats the power pill, then the state of the ghosts changes and they change colour. They then try and flee away from the Pac-Man, and when the Pac-Man catches them, it eats them. So substantially different behaviour because of a switch in state. The example I was going to show you today is involving traffic lights and involving what we call in the UK a pelican crossing, which is simply an abbreviation for pedestrian light control crossing. It's just what we have in the UK for the sort of crossing where the pedestrian has to press a button, wait for a bit, and then the lights will go and the traffic will stop. And so I've got a WPF application here to simulate that. I'll just run it up so we can see it from the start. And so there we can see we've got the graphics representing the lights for the traffic and also the lights for the pedestrian. Pedestrian comes along, presses the wait button, that lights up. After a few seconds, we go through the steps, the traffic stops. Then something we have in the UK is we have this flashing light just to indicate the traffic's about to start again, so to tell everyone they need to get going. Not every pelican works like that, but quite a lot of them do. We can see some variations later on. And then we go back to the start position. Now, with any stateful situation, something that we very often do is draw a UML state diagram. And so we can see that represented here. And it's a pretty simple diagram. That circle simply represents the start state, and we can see from the start state we just go straight into what I've called go idle. So we can actually see that there are 6 possible states that our pelican can be in: go idle, go waiting, prepare to stop, stop, prepare to start, and re-request. And we can also see that there are 2 possible actions. So there's either press, when the pedestrian presses a button, or there's timeout, which is simply a timer that moves us through the phases and we count as an external action. And whatever complexity of a state model you have, it's essentially going to consist of those 2 things: a number of actions, 2 of them in this case, press and timeout, and a number of states. And if we just run that up again, we can walk it through those. So we start out in go idle, just the green light displayed, and then if I press, we move to go waiting, no visible change, but then the timeout takes us to prepare to stop, then the timeout takes us to stop, then the timeout takes us to prepare to start, the flashing, and then we can see the timeout takes us back to go idle, and we're back where we started. The other thing we can do, that re-request, happens if we take it through the process again. Then when we're in the prepare to start, it's possible for me at that point to press the button, the wait light will go on, and now, after the wait, it will go round again. Pressing the button in any other state doesn't do anything because we're already going through the process, but it's only in that one that we get the re-request. So that's our state model, our state diagram. And that can be implemented in many, many different ways. So the implementation I've got here to start with is actually a very basic one, which, although it works, is not particularly good style. So what we've got here is this pelican class, and then we've got an enum representing those states. So we can see that enum, 6 elements, corresponds exactly to the states we had in the diagram. And then our 2 actions, we have the press and then we have the timeout. And in each of those, we have, in this not very well implemented version, a switch statement. So on the press, if we're in the idle state, then the press sets us to the waiting state and we change the light states and we set the timeout. Or if we're in the prepare to start, we go to that re-request, do similar things. And then the timeout basically takes us through each one of the stages that we saw in the diagram of the cycle going round. So it works, and in fact we know it works because I've also got some unit tests here that do things like press and then do 3 timeouts. So again, if we look at the diagram, a press and then 3 timeouts should take us to the prepare to start state, and then we can just check that the lights are correct for that. And we can see we're getting green lights there. And that's important because when I introduce the state pattern as a better solution, we don't want to change the behaviour at all. This is a refactoring, and so we should have green lights before and green lights after. Just to look though at why this really isn't very good in terms of code, it's because we've got what's known as a bad smell, something that you look at the code and you just know that feels wrong. In this case, it's these long switch statements. So switch statements or if-else chains would be another way to do it, are often a sign of bad coding because they're difficult to maintain. Whenever we add a new state to this system, we've got to add it to the switch statement in timeout and add it to the switch statement in press. Or if we add a new action, then we've got to duplicate all of that code. So it's really messy and it's often a sign of bad coding. Just one other thing to highlight in here that you'll often get with a stateful system is you've got to consider what happens with invalid actions. So for example, pressing the button only makes sense if we're in the go idle state or the prepare to start state. What should we do if somebody presses a button in another state? Well, I think the best solution there is to do nothing because, a user may press the button, it should just ignore them. So that's fine. On the other hand, if we have a timeout, we should never get a timeout in the go idle state. And so what I've done here is just done a default where with the timeout, if it gets a timeout when it's in a state that's not expecting a timeout, it will just throw an exception because that shouldn't happen at all. Okay, that's the bad way to do it. It works, but it's inelegant, difficult to maintain code. It breaches, in fact, both the single responsibility principle and the open-close principle in that we have multiple reasons for change. If we do change, we're going to do it by modifying this existing code, not adding new classes. What we're going to do then is this gang of 4 pattern, the state pattern. And what we can see here, if I just switch to a UML diagram, this is what we're going to introduce. We're going to do what we so often do when we're refactoring, when we're applying good design principles, we turn things into classes. So the concepts that we previously had of the states, go idle, go waiting, that we had implemented as case clauses, we actually implement as classes. Each one of those states becomes a class, go idle state, go waiting state, and they're derived from a base class called pelican state base. So this isolates each one of the states into its own class, which now means we are going to obey the SRE and the OCP. If we need to change one, we're just changing one class, one reason for change. If we need to add something, we add a new class. We don't modify existing classes. So let's put all of that together. And what we need to do, we'll firstly just add ourselves a folder that we'll call states. And then into there, we'll add a class and we'll start out with this base class. So this is our pelican state base. And that needs to be an abstract class. We're never going to have one of these. And it's going to have a property, which is going to be a protected property of type pelican. So this is the pelican that all these states are going to operate on. Call it pelican, and it's going to be get only, so that the derived classes are going to be able to access it, but it's actually going to be set up in the constructor. So we'll pass that in there so that every one of these has a pelican it can deal with, and we'll just initialize that in there. One other thing we'll do in the base class, if you just take a look at the pelican, you'll notice that in all of the cases, the very first thing we do is just turn off all the lights. So we don't have to worry about which ones are off. We just assume everything's off. Then we only turn on or set flashing the lights we want to change. So also in our pelican state base, I'm just going to say pelican dot, and then we'll just do that all off so that we just get a clean sheet each time. And then the other thing we've got to do in our pelican state base is we've got to provide the action. So remember, we've got two actions in this case. We've got the press and we've got the timeout. So the first one we're going to have is our press. So public virtual void press. What should happen in the base class for press? Well, remember what we said. If you press the button when you're not in the appropriate state, what should happen is nothing. So we can just leave that as blank and put that in there. On the other hand, the other action we were dealing with was our timeout. So here we're going to have a public virtual void timeout. And in that case, remember, it was actually going to throw an exception because we said that's definitely an error. So here I'm just going to say throw new invalid operation exception. And then we'll just say something like pelican is in wrong state. Don't know what state it is, but we just know it's the wrong one. That's the default. So that's our base class sorted. And then remember back on the diagram, what we had here was that the pelican state base is referenced by the pelican. So we go back into the pelican now, and we're no longer going to be using this enum pelican states. We're going to replace that with this pelican state base. Get the namespace. And that's obviously going to break a load of things, but we'll get them fixed by the time we've got it all finished. So now we need to start adding some concrete states. So let's start with the go idle. And this needs to be derived from our base class. And that means it's going to need a constructor to take the pelican and pass that down to the base class. Then we've got to consider what happens in the go idle state, and we can do this either by looking at the existing pelican code or by looking at our diagram, and we can see that in the go idle state we're never going to receive a timeout. We're only going to have that press, and so we only need to override that one. So back in here we'll do an override of press, and then we've got to decide what we do with that. Well, if we look at the existing code, we can see one of the slight problems here. There we are in the go idle state, and we've received the press, so we move to the go waiting state. So that's one thing we've got to do. But then this code here, setting the lights and setting the timeout, those are actually the lights and the timeout for the go waiting state, for the state we've just moved into. And so this is a bit confusing, really, in that it's a bit unclear when we see go idle there and go waiting there, what these refer to. This bit of code actually is much better placed in the constructor, in this case for the go waiting state. If we just go and find where we transit to the go idle state, which is what we've got there, then actually that is the code that should go in the constructor for the state we've moved to, the go idle state. So if I copy that, go to our constructor here, and then no longer this because we're not inside the pelican, so I've just got to change that to pelican. So whenever we go into the go idle state, we're guaranteed to get the green light on and the red figure on, which is what we want. And then in the press, all we've actually got to do is what we had here, which was to change the state to go waiting. So we could take that code. First thing we've got to do there again is pelican dot, because it's a member of pelican. And then the other thing is we're no longer using that enum, so that is going to change to a new go waiting state, which we haven't written yet, but just like we've got here, we know it's going to have to take that pelican as a parameter to the constructor once it gets going. So that's our basic template. We have to have the setup which turns on the appropriate lights, and then in this case just the press which moves us on to the next state. Let's do the next one of those. So that's going to be our go waiting state. So we will add a class there called go waiting state. And then in fact let's save a bit of time with some copy and paste. So let's grab that one, put it in there, change the name to the go waiting state, get the namespace, tidy that up a bit. But then of course the behavior is going to be different in a couple of ways. One is in the go waiting state, again back on the diagram, we don't ever have a press, we're only going to have the timeout. So we'll get rid of that press and instead we'll override the timeout. Again, on the timeout, what we need to do is move on to the next state. So that's going to be pelican.state equals new, and then that's going to move us on to the prepare to stop state. Again, not written yet. And so the constructor here then, if we go back to the pelican, when we go into the go waiting state, that's what we've got to do. We've got to set the appropriate lights and also, in this case, set the timeout. And once again, all those are now members of Pelican. And so you can see that although we still haven't written the prepare to stop state, if you look at the go idle state, that's now happy with the go waiting state. And so we could just process all of those, basically looking at the diagram or taking code from the Pelican. As you might expect, I've prepared that earlier. So here's our 4 other states. So if we just drag those in there, those should all be complete now. The one that's probably just worth noting there is we've only got the one state actually, which receives both the timeout and the press, which is the prepare to start. And so if we look at prepare to start, we can see that is the one that actually has to implement both of the actions and sends us off into different states in different cases. Right then, we're almost there now. We'll go back to our Pelican and we'll do the fun bit, which is completely delete those switch statements. So the body of timeout, the body of our press can go completely, because all we now need to do is we need to, on the press, again if we look at the class diagram, the methods on the Pelican just delegate directly to the equivalent method on the state object. So all we need to do here is say state.press. All we need to do here is say state.timeout. This is one of those situations where I really like to use these relatively new in C#, the expression bodied members, where you use the lambda symbol. And I like it here because it really emphasizes to anyone reading the code that this is pure delegation. You should never be adding any other functionality to the Pelican's press because it's all delegated to the state's press. So that's just quite a neat use of those. So we've set those up. Got to do a couple of other things. We've got to create an initial state. Again, it all comes from the diagram because here we saw the initial state, the circle, takes us into go idle. So we're just here, we'll say state equals new go idle state, passing this in because it's got to take the Pelican. That means we can remove that bit of code, which was the previous way of initializing the lights. That should all be done now in the constructor. Remember, that's what happens there. And now that should all work. How do we find out? Well, let's run the tests. We had green lights before, we got green lights after, so that's proved its work as refactoring. Or if we run that up and click the button, we can see it's going through the paces in exactly the same way as it did before. So we've not made any changes to functionality, but we've done a refactoring that I think puts this code on a much, much more elegant footing. If we look at our Pelican now, it is extremely simple. In fact, we can simplify it a bit further. We can get rid of that enum because they don't represent the states anymore. And then the code is far simpler. We've just got a few things to manipulate lights. We've got to manage the timeout, but all of those switch statements are now completely removed, and we have used polymorphism to make the decision between the states. And then if we look at the states themselves, each one is isolated, so obeying the single responsibility principle very, very closely. And we can look at something like the prepare to stop state, and we can see that it will have the wait light and the amber light and the red figure on. It will stop for a certain amount of time. When the timeout comes, it moves to the stop state. So if we need to change any of that, it's absolutely isolated. And in fact, just one example of that, we saw when we run this up at the moment, what a lot of UK pelican crossings do is, as we can see here, when they're about to get going again, we've got these flashing lights. So that's actually telling the drivers they're allowed to drive if there's no one on the crossing, and it's telling pedestrians that they can finish crossing, but they shouldn't start crossing. Some other lights work in a slightly different way. Some of them will have it that rather than having the flashing light for the traffic, they have red and amber on at the same time. And now we've isolated this, that's so easy to do. So if I want to say when we're in the prepare to start state, then we should have the amber light as on, and we should have the red light as on, and the green figure is flashing. Well, that's all we need to do. It's so isolated, and that shows us the benefit not just of this pattern, but of the idea of the single responsibility principle. And so now, having done that, we'll see that we get the red and amber light rather than the flashing amber light. So a simple way to change it. So there we have it, the state pattern. What we did there was we removed the complexity of the switch statements that we had that were hard to maintain, that breached the single responsibility principle and the open close principle, and we put those into individual classes. Although it's still quite complicated, the isolation into classes makes things much easier. It's not the only way to implement a stateful object like the pelican, and next time we'll see an alternative, a thing called a finite state machine, and we'll look at the pros and cons between the two approaches. Any questions, pop them in the comments section. Do subscribe. I'll see you next time.